Hello dear students. Today we will be discussing the topic piezoelectric transducers and then we will move on to strain gauges as well as load cell. So piezoelectric transducer is used for conversion of pressure or mechanical stress into a force. So again the physical quantities like force, pressure, stress, etc. can be measured using piezoelectric transducer. It converts the physical quantity into electrical voltage. So you will be getting the output in terms of electrical voltage, and it has some polarized elements within this. So we are making use of this polarized element, and the crystal structure is a specific type of crystal structure, and you will be attaching the electrodes at the opposite faces where you are opposite to the faces where you are applying the pressure, and you will be getting the output. And generally elements like quartz, SiO2 or barium titanate will produce electric field when material changes the dimension as a result of the mechanical force, and this particular effect is known as piezoelectric effect. And quartz as well as barium titanate are the general examples of piezoelectric materials. So here you can see that this is a normal figure A is a normal piezoelectric material. You can consider this as a quartz element, and once you apply tension and so stretch it, you will have voltage generated in one direction in this polarity with this polarity, and once you compress it, you will have a reverse polarity. Okay, so this is what your piezoelectric effect is all about, and this is clearly based on the crystal structure as well as the orientation of different elements in the crystal structure. Now we'll look at how this effect can be explained. Now this you can consider this as the quartz structure. You have considered one portion of the quartz structure where you have silicon as well as oxygen atoms available. So silicon is considered more positive and oxygen is considered more negative. Relative charges is given here, and the net effect is that the atom remains in a neutral position. And if you consider any one charge, I will take positive charge, the neutral, the net center of charge, just like a center of mass you have learned in the mechanics, you can consider center of mass. So it will be somewhere here. Okay, it will be coinciding somewhere at the center where you have a neutral positive charge. You have no charge. All the net value of all the positive charges will be at this center. Okay, and this balances out with the negative charges, so you will have a neutral effect. Now what happens once you stretch it? Once you have a tension, once you stretch it, your positive charges will be moving in this direction, and once you move in that direction, what happens? Your net center of mass will be or your net effect is that your center of mass will be slightly moving, center of charge will be slightly moving upwards. The balance is lost, and slightly your center of charge will be moving upwards, so that you will have a net positive charge at the top side and your net negative charge at the bottom side. Relative values, relatively will have a negatively charged section at the bottom side. So you can think something like this. You have a charge here, and this is your state of center of charge, so that will be a little higher when compared to the first image. Similarly, when you compress it, what happens? Your positive charges will be compressed like this, and this particular charge will be moving downwards, this positive atom. Okay, and hence your center of charge will be shifted downwards, so that your net positive charge will be at the bottom surface and your net negative charge will be at the top surface. Just like you have done the analysis for positive charges, you can do it for negative charge silicon atoms, oxygen atoms also. And in doing so, you will see that your net center of charge of negative charges will move upwards. And so in that way, you get a net negative charge at the top surface. So that's how the entire piezoelectric effect is there. Now this is only a single part of the, or single element of a single section of the quartz structure. So you will have a number of such elements joined together in three-dimensional form to get the entire quartz structure. Now this is an example for piezoelectric material that we use in our day-to-day life. So this is a lighter. Here you have a piezoelectric element which produces a spark, a voltage, a spark between the 2 points. So here we have two end points conductors, and here we have a spark between these two conductors, and you are spraying fine particles of fuel, whatever the fuel that you have, into this gap, and you have a flame coming out. It's a controlled flame. So this is one of the applications of piezoelectric material. And electrostriction is an opposite phenomenon of piezoelectric material, where once you apply a electrical source, apply a voltage across the quartz structure, you will get compression or expansion depending on the polarity of the source. Okay, so if you are applying an AC source, you will have compression as well as expansion, both happening in just like cycles. Okay, and the dimensions will be changed depending on the magnitude of the source. So this is known as electrostriction, which is exactly opposite of piezoelectric effect. Now these are some of the modes of applications of piezoelectric transducers. So these are thickness shear, phase shear, thickness expansion, as well as transverse expansion. So the arrow shows how you are applying the force. So if you apply the force in this direction, one force is applied like this and the other is like this at the face. So you can take out the voltage like this. The terminals are shown here. Similarly, once you apply the voltage along the edges, along the corner edges, again this is known as phase shear. And in a normal case, once you apply a tension, you get a voltage, and once you apply a tension in the side faces, you also get the voltage. So these are all depending on how you cut the quartz structure. You have to cut, or you have to manufacture quartz structure in specific way that it produces this particular effect. Now, some of the applications of piezoelectric transducers can be used for dynamic measurements like surface roughness, acceleration, and vibration. It is used in oscillators, and it can be used in microphones and speakers. So it is used in both sides. Just like a microphone and speaker works on the same principle, here also piezoelectric effect as well as electrostriction can be used in both microphones as well as speakers. This can be used for as an ultrasonic generator, and they are also used in seismograph to measure vibration in rockets. So you can look at this reference and see for yourself the details of the applications. Then you have piezoelectric transducers. The advantages: they do not require any external power. These are active kind of transducers, and they have good frequency response, rugged in construction as well as small in size. And the output is very low, and which in turn becomes a disadvantage for the transducer. So you have to have some external circuit to smoothen or condition the output. It is used for dynamic measurement only. That is, it is generally used for varying quantities, measure the varying quantities. It has good temperature sensitivity. It has high temperature sensitivity in the sense it is highly variable with respect to temperature. As the temperature varies, the output also is dependent on the temperature, and some of them are water soluble and is affected by the humid environment. Now we'll look at the next type of transducer, which is a strain gauge. Now strain is a measurement of deformation which represents the displacement between particles in a body relative to a reference length. Now we are trying to measure the strain with the help of strain gauge. So strain is defined as the change in length per unit length. Now this is a passive transducer which converts the mechanical displacement into a change of resistance, and we are trying to measure this resistance with the help of some conditioning circuits, and accordingly you will get the output voltage, which is a function of the strain. It is a thin wafer-like device which can be attached to a variety of materials, which helps to measure the strain. This is a general structure of a strain gauge. consists of a pattern of resistive foils, which is mounted on the backing material. So you can see that this is the backing material that you have, the blue colored one, and these white colored ones are the resistive foil which is being placed. And once the strain is attached to or applied to the metallic wire, the dimension changes and the resistance varies. So here you can see that this is a thin center portion where your measuring grid is connected and your leads are also provided. So once you apply the strain, the material will be under pressure and the dimension changes and the resistance varies, and the change in resistance can be measured. Now there are two types of strain gauges. One is electrical resistance type strain gauge and the other one is semiconductor type strain gauge. Now in resistance type strain gauge, you have two types of strain gauges, unbounded and bounded. Now unbounded strain gauge is generally used for measuring displacement between fixed as well as a moving structure. And here you can see that one of the structure is fixed. Suppose this particular structure is fixed and this is a moving one. So we are making use of this strain gauge to measure the strain between a fixed structure and a moving structure. Now the two wires are in compression. You have 4 wires available. So 2 are in compression and 2 are in expansion or tension. So in that way you get the strain measurement. Now in bonded type of strain gauge, as we have already seen, you have two types, which is made of wire type as well as foil type. So here this kind of strain gauges or wires are embedded into the backing material in the form of grid, and these are fixed type. You can directly use to measure the strain of a particular section by attaching this particular strain gauge to that position. Okay, and you are making use of photo etching technique to obtain this particular structure. Now another type of strain gauge is semiconductor strain gauge. So here we are making use of semiconductor materials like silicon or germanium, and here the property that we use is piezo-resistive property. That is, once you apply the force, the resistance varies in a semiconductor, and we are making use of that property to measure the force or the strain. So here you can see that you have a semiconductor material and the base material is also available here, or the contact or the below material is the base material. Onto the base material we are mounting the semiconductor material, and we are providing the electrodes to take the output. And it has a high gauge factor, and it is very small in size. So that is one of the advantages of a semiconductor strain gauge. Now here you can arrange the strain gauge in different forms. So here the arrangement is known as rosette arrangement. In rosette arrangement, you will be arranging the strain gauges in different directions to obtain strain in different directions. So your strain also will be in different directions in different positions. So you will be using the strain gauges in different arrangements to obtain strain. So here you can see that these two strain gauges are arranged in 90 degrees. Here also it is in arranged 90 degrees, but it is not overlapping. Here they are connected arranged in 60 degree each, and here also here they are connected in 45 degree each, and you have another strain gauge which is perpendicular to this strain gauge. Okay, anyway, these are all different arrangements by which you can arrange the strain gauges to measure the strain in different directions or different alignments. Okay, now how do you actually make use of the strain gauge? So here you have a test specimen. Okay, and test specimen, suppose the strain gauge is arranged like this. Okay, so here you have a quarter bridge circuit as well as a full bridge strain gauge circuit. In a quarter bridge circuit, what happens is that you connect the strain gauge in one of the bridge arms, and once the test specimen is compressing, you apply the force. Here you will have a change in dimension, and resistance varies. So that change in resistance can be identified with the help of balancing of the bridge, or depending on the voltage that is being generated at this galvanometer, you can identify the strain that is there. You can relate the strain with the voltage. Now in a full bridge circuit, you will have strain in all the four strain gauges in all the four bridges. In the case of unbounded strain gauge, unbounded wires, you had four wires connected to measure the strain. So there, two are in compression and two are in tension. Okay, so these two are in compression and these two are in under tension. So this can be connected, and the balance, once you lose the balance, that voltage will be generated, and that voltage is an indication of the stress that is produced, okay, or stress that is applied to the strain gauge. So in that way you are able to measure strain with the help of bridge circuit, with the help of strain gauges. Now what you need to work out is, you need to compare bonded and unbonded strain gauge, which you can do it yourself, and also need to find out the advantages of semiconductor strain gauges. Now load cell is a kind of transducer. It's a different kind which measures a force and gives an output in terms of electrical signal. And this load cell is actually an application of strain gauge that we have already seen. So load cell is an entire structure which houses the strain gauges, and it not only uses strain gauges, it can also be used along with hydraulic as well as pneumatic arrangements to measure the force. Now as we already seen, strain gauges usually make use of a load cell, Weiston's bridge arrangement. Now this is a load cell transducer. So here we have strain gauge available inside this, and once you apply the force, some voltage will be generated which measures the strain. Now again we have already discussed the strain gauge measurement. Here we have four strain gauges or sensors which are used, and these four sensors will be connected as four arms of the bridges, and once the force is applied, you will have compression and tension in the strain gauges, and that will be measured with the help of the in terms of voltage that is generated. Now this is a pneumatic kind of strain load cell where you make use of air as the operating medium. So once you apply the force here, a deformation of the material occurs, and that deformation will be transferred into this air or pneumatic medium, and you obtain the force in this meter. Similarly, you have hydraulic load cells also, where a liquid forms the operating medium. The force will be applied, and that particular force will be transferred to the medium with the help of a load cell, and that medium will be now acting to transfer the energy into this measuring device, and you are able to obtain the amount of load that is applied at the load cell. Okay, so that is how you make use of pneumatic as well as hydraulic load cells along with strain gauge type of load cells. Now some of the advantages of load cells are that they are rugged and robust in construction, they have good reliability and stability, they are specially designed to suit the harsh and severe environment, and they are temperature compensated. Strain gauges are may get affected by temperature, but load cells in general are temperature compensated. They have a good stable system with no moving parts, and they can be connected with multiple strain gauges, and any standard bridge measuring circuit can be used along with the load cells, and they have very small side and eccentric load effect. That is, once you have the strain gauge, okay, once you apply the force at the side, you have a strain gauge or a load cell like this. Even if you apply the load at the side, that also can be measured with accuracy. There are some devices which measures force only once you apply it at the center. So that this is known as eccentric load effect. If you have uneven load coming at the surface, eccentric means you are not concentrating the load at any one particular point, or load is not evenly distributed. So in that way also, in that manner also, if you are applying an eccentric load also, you will get the output. So these are some of the advantages of load cell. So thank you so much.